Hello. So last day we were studying about the visible spectrum, how the spectrum of the white light divided into its 7 constituent colors, or rather dispersed by the prism, and this experiment was first performed by Isaac Newton. Today we will deal with the other regions of the electromagnetic spectrum, the so-called invisible spectrum. The visible spectrum constitutes a very small region of the entire electromagnetic spectrum. It only ranges from somewhere around 4000 to 8000 angstrom. And it is only this little region of the spectrum which produces a sensation in our eyes. As a result, we can detect the spectrum which we know as the visible spectrum. For light of any other wavelength which lies within, suppose, the UV rays or the infrared rays, they might affect our eyes, they might damage our eyes, but they will not produce any sensation in our eyes. As a result, we cannot see them the way we see visible light. Now, visible light has a wavelength ranging from 4000 to 8000 angstrom, but there are other regions of the electromagnetic spectrum as well, and we need to know their names, who discovered them, and also the range of the wavelengths corresponding to each region of the spectrum. Gamma rays were first discovered by Becquerel and Curie, and they have a wavelength less than 0.1 angstrom. I suppose you know 1 angstrom is 10 to the power minus 10 of a meter. Next we have the X-rays. X-rays were discovered by William Röntgen, and the wavelength lies between 0.1 to 100 angstrom. Followed by it are the ultraviolet rays, discovered by Professor J. Ritter, and they have a wavelength ranging between 100 and 4000 angstrom. Now we come into the well-known domain of the visible light, the domain in which we stay, in which we see things around us. It was discovered by none other than Isaac Newton, and the wavelength range is 4000 to 8000 angstrom. Followed by infrared rays, which were discovered by a famous astronomer William Herschel, and the wavelength is 8000 to 10 to the power 7 angstrom. Microwaves were detected or discovered by Hertz, after whom the unit of frequency is named, and the wavelength ranges from 10 to the power 7 to 10 to the power 11 angstrom. Finally, we have the radio waves discovered by Marconi, and the range of the wavelength is above 10 to the power 11 angstrom, which is 10 meters and beyond. So this is a table in which you get the name of the radiations, who discovered them for the first time, and what is the wavelength ranges. And you need to know this table, especially the values of the wavelength, because once you know the value of the wavelength, you can easily calculate the value of the frequency. The speed of light, no matter whether it is in the invisible spectrum or the visible spectrum, all of them follow this formula that c is mu times lambda. That is, the speed of light is equal to frequency multiplied with the wavelength. And the speed of light is well known to you. It's 3 into 10 to the power 8 meters per second. And if you remember the wavelength corresponding to this table, then from the formula you can easily calculate what would be the corresponding frequency range. And so if any numericals are asked in the exam which wants to know that, like, what is the frequency range for X-rays, or what is the frequency range for radio waves, you can easily calculate from this formula if you remember the values of lambda. Now this is the electromagnetic spectrum arranged in such a manner that as we go from left to right, the wavelength increases, and as we come from right to left, the frequency increases. So it's quite obvious that in the entire electromagnetic spectrum, gamma rays have got the highest frequency and the lowest wavelength, whereas the radio waves have the longest wavelength but the lowest frequency, and visible light is somewhere intermediate between them. So this was all about the electromagnetic radiation along with their arrangements. Next we shall go into the details of each one of them separately. Now there are certain properties which are common to all of these electromagnetic radiations, irrespective of whether they are ultraviolet, infrared and so on. And we need to know these properties. There is the 5 set of properties which are common to all of these radiations in the electromagnetic spectrum. One of the properties is so for all of these radiations, they travel with the same velocity, that is 3 million kilometers per second in vacuum or air. Each of these follow this one property. The second property is that they are unaffected by electric and magnetic fields. All of them follow the laws of reflection and refraction. They do not require any material medium for their propagation. They can travel through vacuum, but if there is a material medium, they can travel through that as well. And these electromagnetic waves are transverse in nature. So these are the 5 properties. Let us briefly go through them once. So one of the properties is that they have a speed of 3 into 10 to the power 8 meter per second in vacuum or air. So whether it's a radio wave or ultraviolet or visible, it doesn't matter. As long as they are traveling in air and vacuum, they will travel with this speed. Number 2, they are unaffected by electric and magnetic fields. This denotes the electric fields and this denotes the magnetic fields. So they are not affected by any electric or magnetic fields. Number 3, they follow the laws of reflection and refraction. You are well acquainted with the laws of reflection as well as refraction. All these electromagnetic waves, not just the visible ones, follow these laws. And when light travels from one medium to another, such that refraction occurs, you know that its speed changes, and this speed changes due to a change in its wavelength. So the thing that remains constant is frequency. As I have said earlier, that for a light, it has got these 2 characteristics, the wavelength and the frequency. And among them, frequency depends upon the source from which that light or radiation is getting produced. So frequency does not change even if you are traveling from one medium to another, even if refraction takes place. So what changes is wavelength, and they happen for all of them. The 4th property is that they do not require any material medium for propagation. If you provide a material medium, it's fine, but even if there is any, like if they are traveling in vacuum, they can still travel with the speed of 3 into 10 to the power 8 meter per second. And finally, these waves are transverse waves. There are 2 kinds of waves which you studied in class 9. There are longitudinal waves and the transverse waves. So electromagnetic waves are transverse waves in nature. Now we have some theoretical part in here. So let us deal with the theoretical part now. Gamma rays. How were gamma rays first detected? Well, they were detected by Becquerel and Curie, and they were studying radioactive samples from which they found out that these gamma rays are emitted. So gamma rays were mainly emitted from the decay of any kind of radioactive particle, It can be radon, it can be uranium, it can be plutonium. Whenever radioactive decay occurs, gamma rays are emitted from them. And gamma rays are also present in outer space. Gamma ray bursts, it's one of the astronomical phenomena that often happen. And what is the practical utility of gamma rays? Well, one of the disadvantages of gamma rays is that they can cause immense biological damage to the human body. They can mutate the DNA, they can mutate the cells, and this disadvantage of the gamma rays can also be used as an advantage when we treat cancer patients. Gamma rays are used to kill those cancer cells, and they are also used in the industries to check welding, to check if there are any defects or cracks in metal manufacturing, and so on. Next, there are the X-rays. The story of discovery of X-ray is well known to you, how William Röntgen accidentally discovered it by finding the impression of a human skeleton on the X-ray plate. And these days X-rays are widely used for that same purpose, the medical diagnostic purpose, for to detecting if there is any fracture in a patient, if the bones are broken or not, because X-rays, though they can pass through the human flesh, they are obstructed by the bones. Also, X-rays are used in CAT scan, and they are also used to check defects and cracks in metals. Another area where X-rays are used is that X-rays are often used in astronomy. You will find certain X-ray telescopes in use today. Also, X-rays are used to study the specific atomic and molecular structures as well these days. Now we come to the ultraviolet or the UV light. Now ultraviolet, as I already mentioned, that they have a wavelength ranging from 100 to 4000 angstroms, and they were first detected by Professor J. Ritter. And how were ultraviolet rays detected? Well, the scientist who performed a certain experiment, what he did was he made all the lights in the visible spectrum, that is violet, indigo, blue, green, yellow, orange, red. He made all of this incident, on a sample. The sample was of AgCl, that is silver chloride. And at the same time, he did not know that since UV is invisible to the human eye, he didn't know that there is other regions of the spectrum here as well, the ultraviolet region. So the ultraviolet region was also getting incident upon the AgCl solution as well, just like the visible one. So when the visible ones were made incident upon the silver chloride solution, nothing such detectable change occurred. But the moment ultraviolet light was made incident on the solution of silver chloride, the AgCl solution turned violet and then dark brown. So there was a change in the coloration of the solution. The solution, which was unaffected by all the wavelengths in the visible spectrum, got affected by the ultraviolet region, the invisible spectrum. And from there they came to detect UV and also know that these UV rays, they have got a very high chemical activity. They are capable of converting AgCl solution from violet color and then finally into the dark brown color. So from this they came to know that UV light has got a very high chemical activity, and this is the reason that why our Earth's atmosphere has a ozone layer as well, because if the ultraviolet rays from the sun had been able to penetrate the atmosphere and then reach us, then the same chemical activity would have occurred on our human body, on our skin, and we would get affected as well. And that's why the holes in the ozone layer are so devastating. What are the sources of the ultraviolet light? One of the sources is obviously our sun. Apart from that, electric arcs. Here, one of the sources is sun. A second source is sparks, and a third source is electric arc. And to obtain ultraviolet spectrum, we need something known as quartz prism. The prism needs to be made up of quartz material, because if it is made up of glass, glass has this ability to absorb ultraviolet radiation, so it won't produce a spectrum. So in order to obtain the ultraviolet spectrum, we need a quartz prism. And these are the three sources of the ultraviolet radiations, and they have got pretty many other uses as well. They use for sterilization purposes and so on. Next we move on to the visible spectrum. Now the story of how the visible spectrum was detected for the first time is well known to you. I discussed it in the previous classes. But what are the sources of the visible spectrum? While sun remains one of the sources, the other sources are like a simple candle that we burn in our home, the electric bulb, almost any device whose light we can see with our eyes is a source of the visible spectrum. And the visible spectrum has a wavelength ranging from 400 to 800 nanometers. For the visible spectrum, we can simply use a glass prism, because the visible spectrum region, the wavelengths of the visible spectrum are not absorbed by glass. And these are the various sources of the visible spectrum. And what are its applications? Well, the biggest application is photosynthesis, because the plants, they absorb the light from the visible spectrum to prepare their own food. And we know that ultimately via the food chain, all forms of life, almost all forms, are dependent on the plants. That's one of the biggest applications of the visible spectrum. Next we move on to the infrared region. The infrared region of the spectrum. Its wavelength ranges from somewhere around 8000 to 10 to the power 7 angstrom, and this was first detected by William Herschel. And how was it detected? Well, that's a fascinating story. So what happened is, he took 3 thermometers. Suppose these are the 3 thermometers, each of which has got mercury inside it to measure the temperature, and then he made these thermometers, he placed these thermometers in 3 regions of the spectrum. This was the visible region, this was the ultraviolet region, and this was the infrared region. So basically he placed 3 thermometers for 3 separate regions. This thermometer, the ultraviolet radiation were made incident on it. The visible part of the spectrum was made incident on this thermometer, and the infrared region of the spectrum was made incident on this thermometer. And these are the blackened bulbs of the thermometer. Blackened bulbs. For better absorption of the radiations. And he kept on taking observations. After 1 hour, after 2 hours, he came back and took the readings of the temperature. And he found that while in the ultraviolet and the visible region of the spectrum, the temperature increased very normally, in the infrared region there was a rapid and significant increase in temperature. And infrared was not visible, it's still not visible as you know, and at that time he therefore concluded that there must be some region of the spectrum beyond the visible spectrum, beyond red, infrared, which has got this ability of heating effect, which can heat substances up quite quickly. And that is how infrared region was detected by William Herschel. They have this wavelength of 8000 to 10 to the power 7 angstrom. And what are the sources of infrared? Well, one of the sources that remains the same is again the sun. Sun is one of the sources of the infrared spectrum. As for the other sources, well, fire, flame, heated iron ball. These are the other spectrums, sources of the infrared spectrum. The infrared wavelength, it has got an application in various fields, and it is very much associated with us, because you might be studying a topic in a higher class known as the Stefan's law, and there you will know that everybody, including us, you, the camera with which this is getting recorded, all these substances around us, whether living or non-living, they emit a radiation of their own, provided what is the temperature of their body. The hotter the body, the smaller will be the frequency of the, the higher will be the frequency of the spectrum or of the radiation that they emit. The sun is a very hot body, so it emits wavelengths, or it emits radiations having wavelength in the ultraviolet, visible and infrared region. We human beings are comparatively cooler bodies. We have a very less temperature as compared to sun, so the waves that we emit, the radiation that we emit, has got wavelength in the infrared and in the radio wave region. So that is one of the reasons why if you use infrared binoculars or infrared goggles at night, you can see the human beings, as often the military does, or you might have seen in various movies. Those infrared goggles can see the human bodies glowing, because the human beings, they emit wavelengths in the infrared region. Also we emit wavelengths in the radio wave region, and that is one of the reasons that often when we try to tune into a radio, we find that there is some crackling noise, the disturbance happening in the radio sound. That is because the wavelength of the radio waves that is getting transmitted to your phone has somehow interfered with the radio waves that the human body is emitting. So we also emit waves in the infrared and radio wave region, and infrared waves are also emitted by our earth, and that is one of the reasons which has led to global warming and greenhouse effect. But that's a completely different topic, so we shall not delve much into it. Finally, we have the radio waves and the microwaves. The microwaves, well, they have a wavelength ranging between 10 to the power 7 to 10 to the power 11 angstrom. One of the applications of microwaves, it's in almost every household. It is the microwave oven. So that is one of the applications. The other application is they are often used in satellite communication. Finally comes the radio waves, having the longest wavelength, 10 meters or above. One of the applications, as the name suggests, is the radios, on which we can hear various radio platforms, radio stations. Another application of the radio waves is radar communication. Radar, which stands for radio detection and ranging. Radars are widely used in the satellites. They are also used in our GPS and all other kinds of applications. So that was all about the electromagnetic spectrum. We learned about the various regions of the invisible spectrum, which are present all around us apart from the visible spectrum. We learned about who discovered them, what is the range of their wavelengths, what are the properties common to all of them, and how each of them are utilized in various applications in various fields, and how they were detected. The stories behind the detection of UV and infrared has also been discussed today. Next, we shall be studying about the scattering of light and the various applications of scattering of light in our daily life.